Welcome to Fluent Daily, the English listening channel for advanced learners at B2 and C1 level. Every episode features a rich, flowing conversation in natural English on a topic that is genuinely worth thinking about: history, psychology, science, philosophy, and more. There are no simplified sentences here, no slow speech, no vocabulary drills. Just real English spoken naturally on ideas that matter. This is Fluent Daily. Let's get into it.
Today we have a great story, so let's get started right now.
I want you to just picture something with me for a second. Imagine you are standing on a planet, right? But the air around you is thick, it's hazy, and it is completely, totally toxic.
Oh, wow. Okay.
Yeah, so like if you take a breath, it physically burns your lungs because the air is just choked with methane and ammonia. And you look around, and there's absolutely no complex life to speak of. No trees, no birds, no insects, just nothing.
Right, a total wasteland.
Exactly. Now, blink, and I want you to picture a completely different scenario on this exact same planet. You are standing right at the equator, which is supposedly, the hottest part of the globe.
Yeah.
But everything around you is frozen solid.
Just ice everywhere.
Yeah, you are standing on top of a glacier that is over a mile thick. And this sheet of ice just stretches endlessly in every single direction, all the way to both poles. Now, this probably sounds like I'm pitching you, I don't know, a gritty sci-fi movie about some hostile alien world in another galaxy.
Right, yeah, it sounds like Hoth from Star Wars or something.
Exactly, but I'm not.
Huh.
Because that alien world is actually our world. It is Earth's deep history.
And it is a history that, honestly, most of us have a genuinely hard time wrapping our heads around, simply because the time scale is just so vast.
Yeah, it's practically incomprehensible.
It really is. I mean, when we talk about Earth's climate, we tend to think about what the weather was like when we were kids, or, maybe what farmers recorded 100 years ago. But to actually understand the physical machinery of this planet, we really have to look at deep time. Because that extreme chaotic history is, well, it's the only way we can make sense of the invisible levers being pulled today.
Exactly. And that is exactly what we are doing today. If you are listening to this, you are probably insanely curious about how the world works, but maybe you feel a little overwhelmed by the constant noise, the political gridlock, and all the talking points surrounding the climate.
Which is completely understandable. The noise is deafening.
It really is. So here is our mission for this deep dive. We are completely bypassing the daily news cycle and the social media shouting matches. We are going to equip you with a rigorous, purely fact-based understanding of the mechanics of Earth's climate.
Just the mechanics.
Right. We're going to look at the unshakable physics of the greenhouse effect, the historical collapse of past civilizations, and the political economy of why changing our current trajectory is just so incredibly complex.
And we are doing this by looking at the hard data. We are relying on the geological record, the physics that have been settled for, over a century, and documented historical evidence.
No opinions, no spin.
Exactly. This isn't about opinions or policy preferences, at least not yet. It is about understanding the structural mechanics of the planet we happen to live on.
Okay, let's unpack this, because the best place to start is at the beginning, or I guess at least the very deep past. So Earth is about 4.5 billion years old.
Give or take a few million, yeah.
Right. And as we just established with that sci-fi visual, the climate has not been a stable, welcoming place for most of that time. We had that toxic early atmosphere. We had those snowball Earth periods roughly 720 to 635 million years ago, where the planet was essentially a giant floating ice cube.
The literal snowball in space.
Yeah. But I'm trying to figure out how a planet just completely freezes over like that. Does the sun just stop working?
Well, the sun was slightly dimmer back then, sure, but the real mechanism behind snowball Earth is a really fascinating physical process called the albedo effect.
The albedo effect, okay, yeah.
Albedo is just a scientific measure of how reflective a surface is. So when the Earth started cooling, and this is due to a significant drop in atmospheric greenhouse gases, ice caps started growing at the poles.
Okay, that makes sense. It gets cold, you get ice.
Right. Now, ice is white, obviously, so it has a very high albedo. It reflects a massive amount of solar radiation straight back into space, rather than absorbing it as heat.
Oh, I see. So the more ice you have, the more sunlight gets bounced away, which I'm guessing makes the planet even colder.
Exactly, which then makes even more ice. It's a classic runaway feedback loop.
Wow.
Yeah, eventually the ice reaches a critical latitude, and the cooling just accelerates wildly until the ice sheets actually meet at the equator. The whole planet is locked in a deep freeze.
That is terrifying.
And it would have stayed that way forever, completely dead, if it weren't for plate tectonics.
Wait, really? How do earthquakes fix a frozen planet?
Well, volcanoes specifically. Volcanoes eventually punched through the miles of ice, and they started pumping massive amounts of carbon dioxide into the atmosphere over millions of years.
Oh, I see where this is going.
Right.
Yeah.
Because the Earth was completely covered in ice, there was no exposed rock to chemically absorb that CO2, and there was no liquid ocean to dissolve it. So it just built up in the atmosphere.
It's trapping all the heat.
Exactly. The greenhouse effect became so overwhelmingly strong that it rapidly melted the entire planet.
That is wild. The volcanoes basically hit the emergency defrost button on the Earth.
That's a great way to put it, actually, yes.
And then the pendulum just swings completely the other way. We get to the Mesozoic era, right? The age of the dinosaurs. And from what I understand, this was a sweltering greenhouse world.
Oh, absolutely sweltering. There was absolutely zero polar ice. Sea levels were literally hundreds of feet higher than they are today.
And then much more recently, in geological terms, we have the Pleistocene epoch. And this is defined by those recurring ice ages, separated by brief, warm interglacial periods.
Correct. The classic ice age cycles.
So naturally, when people hear this grand, chaotic history of the planet, they bring up a very common trope. They say, look, if the climate has always changed naturally and it has been way hotter in the past, why should we worry about it changing now?
Yeah, it is a question that comes up constantly. And, on a superficial level, you can totally understand why someone might ask it.
It seems logical at first glance.
It does. The historical record clearly shows that Earth's climate is not static. And the natural drivers of these past changes are actually very well understood in atmospheric science and paleoclimatology.
Like what kind of drivers?
We are talking about variations in solar output or massive volcanic provinces that can either release huge amounts of greenhouse gases or, conversely, produce short-term aerosol cooling.
Oh, right, like blocking out the sun with ash.
Exactly. And we also have shifts in ocean circulation, but perhaps most importantly, we have changes in Earth's orbital parameters, which are known as Milankovitch cycles.
Ah, I've heard that term thrown around. Milankovitch cycles.
Yeah.
What exactly is the Earth doing there? Is our orbit just, getting wider and tighter over time?
It's actually a combination of 3 different orbital movements happening all at once. First, you have eccentricity, which is exactly what you just described, the shape of Earth's orbit around the sun slowly stretching from a perfect circle to a slight oval, and then back again.
And how long does that take?
That cycle happens over a period of about 100,000 years. Second, you have obliquity, which is the tilt of the Earth's axis. It slowly rocks back and forth between roughly 22 and 24 degrees, and that cycle takes about 41,000 years.
Okay, so stretching and tilting.
Right, and third, you have precession, which is essentially the Earth wobbling on its axis, kind of like a spinning top that's starting to slow down.
So the Earth is stretching, it's tilting, and it's wobbling, literally all at the same time.
Yes. And the incredibly complex interaction of those 3 cycles slightly changes how much solar radiation hits the northern hemisphere during the summer.
Just subtle little nudges.
Exactly. For the last couple of million years, these subtle orbital shifts have been the absolute pacemaker of the ice ages. They are the initial trigger that nudges the planet slightly cooler or slightly warmer. So yes, natural variation is a fundamental mechanical reality of our planet.
But using that deep time natural variation as a reason not to worry about what is happening today feels incredibly flawed. I was thinking about how to visualize this for you, the listener, and it strikes me as being a lot like driving.
How so?
Arguing that modern climate change is harmless because the climate has changed naturally before is like saying cars can naturally roll down hills, so I shouldn't worry about this one currently accelerating toward a brick wall.
I love that. That is a remarkably useful analogy, but we can actually take it a step further.
Oh, please do.
What's fascinating here is that the deep time context doesn't absolve current emissions at all. It actually proves their power.
Wait, really? How?
Because when we look at those natural drivers of past climate change, like those orbital wobbles we just discussed, they don't mathematically account for the massive temperature swings of the ice ages on their own.
So the wobble isn't enough to freeze the planet?
Not even close. The orbital nudge might start the cooling, but it's the resulting drop in atmospheric carbon dioxide that truly plunges the planet into a deep ice age.
Wait, really? So the orbital wobble just kind of like tips the first domino?
Yeah.
But the greenhouse gases are what actually change the temperature of the whole planet.
Precisely. Greenhouse gases, specifically carbon dioxide and methane, they have always been the primary amplifier and driver of Earth's temperature.
That is wild.
Looking at the deep past provides us with the ultimate baseline. It is the literal laboratory that proves beyond a shadow of a doubt that atmospheric gases act as the master thermostat for the planet.
So whenever they change, the temperature changes.
Every single time. When greenhouse gas concentrations went up in the deep past, regardless of what caused the initial spike, the planet warmed. When they went down, the planet cooled.
So rather than saying it's natural, don't worry, the geological record is actually screaming at us, hey, whenever the levels of these specific gases change, the entire planetary system goes absolutely haywire.
That is exactly what the record shows. The geological history is the empirical proof of concept, and understanding that reality allows us to look at the exact physics of how those gases physically trap heat.
Right, the actual mechanics of it.
Because this isn't some new trendy theory developed by environmentalists in the 1990s. The physical mechanics of the greenhouse effect have been settled for well over a century.
This is a part of the history I find absolutely mind-blowing. When we think of climate science, we tend to visualize supercomputers, satellites, modern laboratories with guys in lab coats.
Sure, that's the modern image.
But we need to rewind to the 1850s. We are talking about the era of top hats, the telegraph, and the American Civil War. There was an Irish physicist named John Tyndall.
John Tyndall is an absolute foundational figure in atmospheric physics. In 1859, he conducted a series of incredibly elegant, yet remarkably simple experiments.
What was he trying to do?
He was trying to understand what the atmosphere was actually doing to the heat radiating off the Earth.
Yeah.
So he built this long brass tube, and he capped the ends with rock salt.
Wait, rock salt? Why not just glass?
Because normal glass actually blocks infrared radiation, whereas rock salt lets it pass right through. So he placed a heat source at one end of the tube and a heat detector, a thermopile at the other end.
I just love how analog this is. He's just shooting heat down a brass pipe on a wooden table.
It was brilliant in its simplicity. He systematically pumped different gases into the tube to see how they interacted with the heat. And what he proved was that gases like oxygen and nitrogen, which together make up about, 99% of our atmosphere, they let the heat pass right through them.
So the detector didn't change.
Exactly. The detector at the end of the tube registered no change. Oxygen and nitrogen are essentially completely transparent to infrared radiation. But when he pumped in trace gases, specifically carbon dioxide, water vapor, and methane, the detector showed a massive drop in heat making it to the end of the tube.
Because those trace gases were actively absorbing the heat inside the pipe.
Yes, exactly.
But why? What is so special about a carbon dioxide molecule compared to an oxygen molecule?
It really comes down to molecular geometry and vibration.
Okay, lay it on me.
Oxygen and nitrogen gases are diatomic molecules. They are made of two identical atoms tightly bound together. They are perfectly symmetrical. Because of this symmetry, when an infrared photon hits them, they can't really absorb the energy.
Just ignore it.
Right. But molecules like carbon dioxide and water vapor are polyatomic. They have 3 or more atoms. CO2 has 1 carbon and 2 oxygen atoms. Because of this complex asymmetrical structure, they can bend, vibrate, and wobble in different ways.
So they're kind of flexible.
Exactly. When infrared energy radiating up from the Earth hits a CO2 molecule, the molecule absorbs that specific wavelength of energy, it vibrates violently, and then it re-radiates that heat in all directions, including back down toward the surface.
They act like a net catching a ping pong ball and just throwing it right back down.
That's a perfect way to visualize it.
And this molecular quirk isn't some malicious feature of the planet. It is a totally life-saving one. Because without this natural greenhouse effect, all the heat from the sun that hits the ground and bounces back up would just, it would just escape directly into the freezing vacuum of space.
It would be lost entirely.
If that happened, Earth's average surface temperature wouldn't be the comfortable 15 degrees Celsius we have today.
Yeah.
It would be roughly negative 18 degrees Celsius.
So without Tyndall's greenhouse gases, we are back to snowball Earth.
The entire planet would be a frozen wasteland.
Yes. This fundamental physics principle is the pillar of why we are even alive to have this conversation right now. It is the absolute foundation of our biosphere.
It's incredible.
But the scientific inquiry didn't stop with Tyndall just proving that these gases trapped heat. If we connect this to the bigger picture, we have to look at what happens when you specifically increase the amount of those trace gases.
Right.
And for that, we move forward to 1896 to a Swedish physical chemist named Svante Arrhenius.
This guy is an absolute legend in the science community because, again, he didn't have a supercomputer. He had a pencil, massive stacks of paper, and an unfathomable amount of patience.
Truly unfathomable. Arrhenius was actually trying to figure out what caused the ice ages. He wondered if a drop in carbon dioxide could explain the massive planetary cooling.
Okay, so how did he prove it?
To figure that out, he essentially spent a whole year performing incredibly tedious, grueling calculations entirely by hand.
Wow.
He had to calculate how much heat would be absorbed at different latitudes, at different times of the year, at different atmospheric concentrations. And remember, this is 1896.
That sounds like a nightmare.
It was incredibly rigorous work. But as a byproduct of this research, he calculated what would happen to the global temperature if you went the other way, if you actively doubled the amount of carbon dioxide in the atmosphere.
And what did he find?
He calculated that doubling atmospheric CO2 would increase the global average temperature by approximately 5 to 6 degrees Celsius.
Which is staggeringly close to modern estimates, isn't it? I mean, for a guy doing math by lamplight in the 1800s.
It is a sheer marvel of pre-computer calculation. Today, using the most advanced supercomputers, incredibly complex atmospheric fluid dynamics models, and thousands of real-time satellite data points, the Intergovernmental Panel on Climate Change, the IPCC, they estimate that a doubling of CO2 from pre-industrial levels would produce somewhere between 2.5 and 4 degrees Celsius of warming.
So he was a little high, but not by much.
Right. This specific metric is what climate scientists call climate sensitivity. Arrhenius was slightly high because obviously he couldn't fully account for certain complex feedback loops, like the exact behavior of different types of cloud formation, which we just understand much better today.
Sure.
But the fundamental physical relationship he mapped out by hand over a century ago remains entirely rigorously valid today.
Okay, so we have the established physics of molecular vibration from the 1850s and the theoretical mathematics of climate sensitivity from the 1890s. But a skeptic might listen to this and say, sure, CO2 traps heat, and CO2 is going up. But how do we know the extra CO2 in the atmosphere right now is actually from us burning fossil fuels? Couldn't just be from volcanoes erupting or ocean vents or some massive natural biological cycle?
It's a very fair question to ask.
Right, and this is where the science gets incredibly elegant. I like to think of it like investigating a crime scene. If a bank gets robbed and you find fingerprints on the vault, you don't just shrug and say, well, billions of humans have fingers, so literally anyone could have done it.
Right. You'd be a pretty terrible detective.
Exactly. You dust the print, you analyze the loops and whorls, and you match the specific fingerprint to a specific suspect. In the atmosphere, we look for what is called the carbon isotope signature. It is basically a chemical barcode floating in the air.
That is an excellent way to conceptualize it. To understand the barcode, we have to look at the atoms themselves. Carbon comes in different isotopes.
Which means what, exactly?
This just means the carbon atoms have slightly different weights based on the number of neutrons they contain in their nucleus. Carbon-12 is by far the most common, but there is also a slightly heavier version called carbon-13 and a rare radioactive version called carbon-14.
Okay, so we have light carbon, heavy carbon, and radioactive carbon. How does this actually prove where the gas is coming from?
It all starts with the plants. When plants photosynthesize, when they pull CO2 out of the air to build their leaves and stems, they are slightly lazy.
Lazy plants, okay.
Yes. They preferentially take up the lighter carbon-12 because it requires slightly less kinetic energy to process chemically. So plant matter has a specific isotopic ratio that leans heavily toward carbon-12 compared to the background atmosphere.
Oh, I see.
Now think about fossil fuels. Coal, oil, and natural gas. They are literally just ancient plants and algae that died, sank into swamps or oceans, and were buried and compressed over millions of years.
Right.
Therefore, fossil fuels are incredibly rich in this specific later isotope, carbon-12.
That makes perfect sense. But what about the radioactive one, carbon-14? What does that do?
That is the final piece of the barcode. Carbon-14 is created in the upper atmosphere by cosmic rays, and it slowly decays over time with a half-life of about 5,730 years. This is actually how carbon dating works for archaeological artifacts.
Oh, okay.
Because fossil fuels have been buried deep underground for tens or hundreds of millions of years, they have absolutely zero carbon-14 left in them. It has all completely decayed away.
So when scientists measure the carbon dioxide accumulating in the atmosphere today, they aren't just measuring the total volume, they are reading this isotopic barcode.
Yes, and what they find is completely definitive. The atmosphere isn't just filling up with generic carbon. The isotopic ratio of the entire global atmosphere is actively, measurably changing. The proportion of carbon-13 is dropping because we are flooding the air with lighter carbon-12. And the proportion of carbon-14 is also dropping, exactly in line with what you would expect if you were pumping massive amounts of ancient, entirely dead, fossilized plant matter into the air.
Which is exactly what we're doing.
Precisely. This phenomenon is known as the Suez effect. It does not match the isotopic signature of volcanic emissions, which have a completely different ratio, and it doesn't match biological emissions from modern living ecosystems because those would still have some carbon-14 in them.
So there's no other explanation?
None. It is a direct, irrefutable chemical fingerprint pointing squarely at fossil fuels.
And the raw data points on the sheer volume of that increase are just striking. For roughly 10,000 years before the Industrial Revolution, atmospheric CO2 hovered around 280 parts per million. Today, as we sit here talking, we are over 420 parts per million.
Which is a massive, massive jump. But to truly, viscerally understand how dramatic a leap from 280 to 420 parts per million actually is, we have to look past our modern instrumental records. We have to read the literal memory of the planet trapped in the ice.
Right, because we didn't have Victorian scientists setting up air monitors 100,000 years ago. So how do we actually know what the CO2 levels were before human history?
We use proxies.
Right, paleoclimate proxies. Basically, nature keeps its own diaries, and if you know how to read the language, you can see exactly what the climate was doing. We can look at tree rings, which grow thicker in warm, wet years.
Yes, dendroclimatology.
We can analyze the shells of microscopic organisms called foraminifera in marine sediments at the bottom of the ocean. We can look at ancient corals, speleothems, which are cave formations like stalactites, and even fossilized pollen trapped in lake beds.
All brilliant proxies.
But the absolute holy grail for this specific atmospheric data comes from the ice. Specifically, the massive Vostok and Epica ice cores drilled in Antarctica.
These ice cores are quite literally time machines. I mean, imagine a place where it is so cold that the snow never, ever melts.
Just piling up forever.
Exactly. Year after year, decade after decade, snow falls and accumulates. As it piles up, the sheer weight of the snow on top compresses the snow underneath into solid ice. But as it compresses, it traps tiny microscopic bubbles of the ambient air from the exact time that snow fell.
So it's basically millions of tiny frozen jars of ancient air.
Precisely. By drilling down miles into the Antarctic ice sheet with massive hollow drill bits, scientists extract these long cylinders of ice. They take them back to sterile laboratories, put them in vacuum chambers, and gently crush the ice to release the air trapped in those bubbles.
And then they just test the air.
Yes. They can directly measure the exact chemical composition of the atmosphere from the past. The Vostok and Epica cores give us a continuous year-by-year record stretching back a staggering 800,000 years.
800,000 years. It is almost impossible for the human brain to conceptualize that much time.
It really is. It encompasses the entire evolutionary rise of our species, Homo sapiens. It covers the entire existence of Neanderthals. And what the analysis of these ice cores shows is absolutely profound.
What do they show?
Over that 800,000-year period, the Earth went through 8 distinct glacial and interglacial cycles, 8 long, grinding ice ages, and 8 brief, warm periods. And across every single one of those cycles, the carbon dioxide levels and the temperature move in perfect, undeniable lockstep.
Side by side.
When CO2 goes down, the temperature crashes. When CO2 goes up, the temperature spikes.
But the key here, the really vital part for you listening to grasp, is the boundaries of that natural variation, because it wasn't just swinging wildly at random numbers.
No, the natural range was strictly bounded by planetary physics. During the absolute depths of the darkest, most freezing ice ages, when mile-high glaciers covered New York and London, global CO2 dropped to about 180 parts per million.
Okay, 180 on the low end.
Right. And during the absolute warmest interglacial periods, it peaked at about 280 parts per million. For 800,000 years, the Earth's thermostat naturally, rhythmically swung back and forth, strictly between 180 and 280.
And today we are 420 parts per million.
Which represents a massive 50% spike above the absolute highest natural maximum of the last 800,000 years. It is an extraordinary, violent departure from the natural rhythm of the planet, and it is occurring in the geological blink of an eye.
Here's where it gets really interesting for us as a species. When we look at that massive 800,000-year timeline, the last 11,700 years stand out like a sore thumb.
The Holocene.
Yes, this recent geological epoch is called the Holocene. And compared to the wild, chaotic temperature swings of the hundreds of thousands of years prior, the Holocene has been bizarrely, unusually stable. It's like the climate just finally leveled out into this perfect Goldilocks zone.
It is a profound realization when you connect this geological reality to human history. Anatomically, modern humans have been around for roughly 300,000 years.
A big chunk of that timeline.
Yes. And for most of that time, our ancestors were living through violent climate oscillations. They were surviving as nomadic hunter-gatherers because you simply cannot establish permanent agriculture when the climate is shifting rapidly.
Right, when rainfall patterns are completely chaotic, or when sea levels are rising or falling by dozens of meters over just a few centuries.
Exactly. But then, roughly 11,700 years ago, the climate flatlines into this beautiful, predictable, stable window.
And what happens? The exact moment the climate stops swinging. We invent agriculture. We domesticate wheat and rice. We build the first permanent cities in Mesopotamia and the Indus Valley. We develop writing, metallurgy, complex trade.
It all explodes at once.
Every single human achievement, the entirety of human civilization, has occurred within this specific, highly anomalous window of climate stability.
We didn't build our global civilization in this climate by accident. We built it because the climate finally stayed still long enough for us to figure out when the monsoons would arrive, when to plant crops, and where to build our coastal cities without the sea level jumping 10 feet every few generations.
So we are perfectly tuned to this one specific era.
We are an incredibly adaptable species, yes, but our civilization is rigidly adapted to a highly specific climate, the Holocene, that we are now actively forcing ourselves out of because of that rapid jump to 420 parts per million.
This raises a really practical question. If we are leaving this historically stable window, how do we know, absolutely definitively, that the warming we are seeing right now today is being driven by our greenhouse gas emissions and not some other natural factor we might have somehow missed?
Right, attribution.
Because there is that 97% consensus among actively publishing climate scientists. And it's an undeniable instrumental fact that we have seen about 1.1 to 1.2 degrees Celsius of global warming since pre-industrial times, and that warming is visibly accelerating. But how do we know it's us? A lot of people still ask, couldn't it just be the sun getting slightly hotter?
It's a very logical question to ask, honestly. If you feel warm, you look at the heat source. But we can definitively rule out the sun, and we do this by looking at the exact physical signature of the warming through the different layers of our atmosphere.
Okay, I want to try to break this down. I've heard this described using a blanket versus space heater analogy. Let's see if I have this right. Let's say you are cold in your house, so you turn on a space heater. What happens physically? The air closest to the heater gets warmest, right?
Right.
So if the sun were acting like a space heater turned up to a higher setting and causing our current warming, we would see the outer layers of our atmosphere, the stratosphere, which is closest to the sun warming first and warming the most.
Correct.
We would also see the biggest temperature spikes during the day when the sun is out, and at the equator where the sun's energy is hitting the planet the hardest. Is that accurate?
Your logic is exactly right for a solar-driven warming event, but that is the exact opposite of what our satellites and weather balloons actually measure.
Wait, really? So what are we actually measuring?
What we actually measure matches the blanket analogy perfectly. Greenhouse gases act like a thermal blanket wrapped around the Earth, trapping the long-wave infrared heat that is trying to escape from the surface.
Okay, so a blanket.
If you are in bed wearing a heavy down blanket, the blanket isn't generating heat, obviously. It is trapping your own body heat. In the atmosphere, because the heat is being trapped from the bottom up, we see the lower atmosphere, the troposphere, where we live and where the weather happens, warming rapidly. But simultaneously, we see the upper atmosphere, the stratosphere, actually cooling.
Wait, the upper atmosphere is cooling. How does that work?
Because that heavy blanket of greenhouse gases in the troposphere is trapping so much heat down near the surface, less heat is actually making it out to the stratosphere.
Oh, wow.
If the sun were the culprit, all layers of the atmosphere would be warming simultaneously. The fact that the troposphere is warming while the stratosphere cools is the absolute smoking gun of greenhouse gas forcing.
That makes total sense.
Furthermore, because the blanket traps heat 24/7, we see temperatures rising faster at night than during the day. And because of the way heat is transported toward the poles, we see the Arctic warming nearly 4 times faster than the equator.
Completely backwards from a space heater.
Every single physical atmospheric signature points definitively not to an external space heater, but to an internal insulating blanket.
That is incredibly clear. It's not just that the Earth is getting hotter, it is getting hotter in a highly specific, uniquely identifiable pattern.
And the precision of these physical observations is striking. When the IPCC publishes their assessment reports, synthesizing thousands of peer-reviewed studies from hundreds of scientists across dozens of countries, they aren't just making educated guesses. They are looking at how perfectly the physical reality matches the thermodynamics models. The melting land ice, the rising sea levels, which, by the way, is largely driven by thermal expansion, meaning the ocean water physically expands as it warms up, the changing acidity of the oceans as they absorb excess CO2, the increased frequency of extreme weather events. All of this aligns flawlessly with the predicted mathematical pattern for greenhouse gas forcing.
Not for solar forcing or natural orbital cycles.
Not at all. The evidence is simply unequivocal.
So knowing definitively that human forcing is altering the climate, and knowing we are exiting that stable Holocene window that allowed civilization to flourish, we have to look at what this actually means for us on a practical level.
The societal impacts.
Yeah, exactly. We have to ask what happens to human societies when the climate shifts rapidly. And honestly, looking back at the historical record provides some pretty terrifying concrete answers.
It does. I think the biggest misconception we have is that we often think of climate change as something gradual, a slow linear creep of slightly warmer summers.
Yeah, boiling a frog.
Right. But the paleoclimate record shows us that the Earth's climate system doesn't always act smoothly. It can shift abruptly. It has tipping points.
Let's talk about one of the most famous ones, the Younger Dryas. This happened about 12,900 years ago. What exactly was it?
The Younger Dryas is a classic, terrifying example of an abrupt climate transition. At the time, the Earth was gradually warming out of the last ice age. The massive ice sheets that covered much of North America and Europe were melting, and human populations were spreading.
Things were looking up.
But then, an enormous glacial lake in North America, known as Lake Agassiz, which had been dammed up by a massive ice sheet, suddenly burst. It dumped an unfathomable volume of fresh, freezing meltwater straight into the North Atlantic Ocean.
Okay, I'm struggling to connect the dots here. Why does a massive pulse of fresh water in the ocean matter so much? Does it just freeze everything because the water's cold?
It's not about the temperature of the water at all. It's about the density. This goes to the fundamental mechanics of the ocean currents. Specifically, it disrupted the Atlantic Meridional Overturning Circulation, or the AMOC.
The AMOC.
Okay, this is a massive system of ocean currents that acts like a global conveyor belt. It transports warm, salty surface water from the tropics up toward the North Atlantic. That warm water is actually what keeps Europe relatively mild today compared to Canada.
Right.
But this entire conveyor belt relies on a specific physical process. When that warm, salty water reaches the North Atlantic, it cools down. Because cold, salty water is extremely dense and heavy, it sinks to the bottom of the ocean, pulling more warm water up behind it.
So it's completely driven by the heavy water sinking. What happens when you dump a literal lake's worth of fresh water into that system?
Well, fresh water is much lighter and less dense than salty water. So when that massive pulse of fresh meltwater hit the North Atlantic, it just sat on the surface like a cap. The surface water could no longer sink.
Oh, no.
The engine of the AMOC stalled. The entire conveyor belt essentially broke.
And what was the result of that conveyor belt breaking? Did it take thousands of years for the climate to change?
No, and this is the most alarming part. In just a single decade, within the span of half a human lifespan, temperatures in the North Atlantic region plummeted back to full glacial conditions.
A single decade.
10 years. The warming trend violently reversed. Ecosystems crashed. It stayed locked in that sudden freeze for 1,200 years before warming up just as rapidly. It is the ultimate proof that the climate system does not always respond linearly to a push. Sometimes it just snaps.
A decade.
Yeah.
That is unimaginable. So what does this all mean for people actually living through it? We can look a bit closer to our own time, during the Holocene. Look at the 8.2 kiloyear event about 8,200 years ago.
Very similar mechanism.
Right. It was a freshwater pulse. It caused a sudden severe cold snap that completely disrupted early agriculture in the Neolithic Near East, forcing massive population migrations because they literally could not grow food anymore. Or take the 4.2 kill-year event.
The 4.2 kill-year event is fascinating because it wasn't a sudden cold snap. It was a devastating, prolonged global mega drought, and its fingerprints are all over the archaeological record across the globe.
Really? Like where?
It is strongly linked to the complete systemic collapse of the Akkadian Empire in Mesopotamia, massive social disruption, and the fall of the Old Kingdom in ancient Egypt, and the sudden decline of the highly advanced Indus Valley civilization.
Just massive societal upheaval. And if we move even closer to today, we have the Bronze Age collapse around 1200 BCE. This is considered one of the greatest mysteries of history.
It's a huge turning point.
You had this incredibly complex, interconnected network of powerful empires in the Eastern Mediterranean. You had the Mycenaean Greeks, the Hittites in Anatolia, the Egyptians, the Babylonians. They had intricate global trade routes, sophisticated diplomacy, highly specialized economies.
The first truly globalized region.
Exactly. And within a very short span of time, maybe just a few decades, almost all of them completely collapsed into a dark age. Palaces were burned, writing systems were entirely forgotten. For a long time, historians blamed mysterious invaders called the Sea Peoples, or catastrophic earthquakes. But modern proxy records give us a very different answer.
Yes. By reading stalagmites in places like the Sorek Cave in Israel and looking at ancient fossilized pollen across the Mediterranean basin, paleoclimatologists found that a massive, prolonged, multi-century drought hit the entire region simultaneously.
Wait, so a drought took out all these massive empires?
What's vital to understand here is the cascading failure. Climate change didn't just cause a bad harvest or two. It destabilized already stressed agricultural systems across multiple regions at the exact same time. The crops failed, which led to widespread famine.
And hungry people get desperate.
Exactly. Famine led to the breakdown of vital trade networks. Suddenly, no one could trade grain for bronze. That led to complete economic collapse, which sparked civil unrest, violent rebellions, and the mass migration of desperate, starving populations, which is likely who those mysterious sea peoples actually were.
They were climate refugees.
Yes. The Bronze Age societies were highly specialized and interdependent, much like our modern globalized world. When the climate broke their fundamental agricultural foundation, the entire complex system shattered.
That is deeply unsettling, because it brings us to the most crucial, pressing part of this deep dive. If a prolonged regional drought could systematically dismantle the interconnected Bronze Age empires, what are we projecting for our global, hyper-interconnected civilization in the 21st century?
It's a sobering question.
Because we aren't facing a localized drought, we are facing a rapid, global, energetic shift.
To understand the 21st century projections, we really have to look at the emission pathways meticulously mapped out by the IPCC. The future of the climate is not predetermined. It is not a set destiny. It depends entirely on the volume of greenhouse gases humanity chooses to emit from this point forward.
So it's up to us.
Entirely. The IPCC generally contrasts two main types of scenarios: aggressive decarbonization pathways that aim to limit warming to roughly 1.52 degrees Celsius above pre-industrial levels, which are the stated targets of the Paris Agreement, and high emission, business as usual, pathways that could produce 3 to 5 degrees Celsius of warming by the year 2100.
I want to focus on that 1.5 degree target first, because it's often talked about in the media as the safe limit, the goal line we are trying to stay under. But when you actually read the physical projections, 1.5 degrees is far from benign.
Not benign at all.
And honestly, given the lag in the climate system, we may already be locked into hitting that number no matter what we do today. Even at 1.5 degrees, the models show drastic shifts in human livability.
The term safe is entirely relative here. At 1.5 degrees, the physical mechanics of the atmosphere change significantly. We must consider the Clausius-Clapeyron relation.
Clausius-Clapeyron, I think I'm saying that right. What is that?
You are. It's a fundamental physical law stating that for every 1 degree Celsius increase in temperature, the atmosphere can hold about 7% more water vapor.
7%.
Yes. This completely alters the global hydrological cycle. It means that when it rains, it pours with unprecedented destructive intensity, leading to massive, unprecedented flooding. But conversely, because the hotter air acts like a giant sponge, it sucks moisture out of the soil faster, turning normal dry spells into crippling multi-year flash droughts.
So the wet places get catastrophically wetter, and the dry places get devastatingly drier.
Exactly.
We are also looking at 0.3 to 0.6 meters, so roughly 1 to 2 feet of baked-in sea level rise by 2100. And that threatens major coastal cities, not just with flooding, but with saltwater actually intruding into their drinking water aquifers.
A huge problem for coastal agriculture, too.
Plus, at 1.5 degrees, we're looking at severe degradation, if not total loss, of global coral reef systems.
The coral reefs are a prime example of biological vulnerability. It's not just the heat causing coral bleaching, it's ocean acidification. As the oceans absorb our excess carbon dioxide, the water chemically changes, becoming more acidic. This literally dissolves the calcium carbonate that corals use to build their skeletons. Millions of people rely on those reef ecosystems for their primary source of protein and for physical protection against coastal storm surges. The impacts of even 1.5 degrees will fundamentally reshape global agriculture and coastal geography.
And I think if you're listening to this on your commute right now, this is probably incredibly heavy to hear.
Yeah.
But there is a profound distributive injustice here that we absolutely have to acknowledge.
It is a critical part of the conversation.
If you look at the map of who is going to suffer the most immediate, devastating consequences of these shifts at 1.5 degrees, it is heavily, disproportionately skewed toward populations in the global south.
Yes.
These are nations and communities that historically contributed the absolute least to the cumulative emissions driving the problem. They didn't burn fossil fuels for the last 150 years to build immense industrial wealth, but because of their geographic location and economic vulnerability, they are the ones catching the first and worst wave of the consequences.
This distributive injustice is a massive complicating factor in international climate negotiations. It is the ethical core of the debate. But as sobering as the 1.5 degree scenario is, we must rigorously acknowledge the current data. Humanity is not currently on track to meet it.
Not at all.
If we look at the current national pledges and actual implemented policies, so what countries are actively doing right now versus what they promise to do in the distant future, we are on a trajectory for roughly 3 to 4 degrees Celsius of warming by the end of this century.
3 to 4 degrees. What does that actually look like on a planetary scale?
A 3 to 4 degree world is an entirely different planet. It is a state the Earth hasn't seen in millions of years. At that level of warming, the risk of crossing those irreversible climatic tipping points we discussed earlier, like the Younger Dryas, but on a global scale, becomes severe. We're looking at the likely irreversible disintegration of the West Antarctic ice sheet.
Wait, how does an entire ice sheet just disintegrate? Doesn't it just slowly melt from the sun hitting it?
It's actually melting from below. The West Antarctic ice sheet is largely grounded on bedrock that is physically below sea level, and the bedrock slopes downward as you go inland.
Oh, a reverse slope.
Right. As the ocean warms, warm water gets underneath the ice shelf, melting the grounding line where the ice meets the rock. Because of the reverse slope, once the warm water gets in, it lifts the ice off the rock, allowing more warm water in, pushing the grounding line further and further back in an unstoppable physical retreat.
It just unzips.
Exactly. That ice sheet alone contains enough water to raise global sea levels by several meters over time.
And we are also looking at biological tipping points, right? Like a potential dieback of the Amazon rainforest, where heat and drought cause the entire ecosystem to collapse.
A total regime shift.
It would transition from a lush rainforest to a dry savanna, turning one of the world's greatest carbon sinks into a massive source of carbon emissions as billions of trees die and rot. But honestly, it's the permafrost that genuinely keeps me up at night.
Yes, the permafrost carbon feedback loop. Across the Arctic, in places like Siberia and northern Canada, vast tracts of frozen soil, called permafrost, contain thousands of years' worth of dead plant and animal matter that never decomposed because it was locked in the ice.
It's just stored organic matter.
Right. As the Arctic warms, and remember, due to the loss of reflective sea ice, the Arctic is warming much faster than the rest of the planet. That permafrost thaws. When it thaws, dormant microbes wake up, begin to feast on that organic matter, and release it directly as methane and carbon dioxide.
And methane is an incredibly potent greenhouse gas.
Well, over a 20-year period, methane is roughly 80 times more effective at trapping heat than carbon dioxide. So the permafrost thaws, releasing methane. This causes more warming, which causes more permafrost to thaw, which releases even more methane.
Another runaway loop.
Once that biological feedback loop truly engages on a massive scale, it acts as an accelerator that humanity has absolutely zero ability to turn off, no matter how fast we cut our own emissions. At 3 to 4 degrees, the frequency of conditions that fall completely outside the evolutionary experience of current biological systems and the adaptive capacity of our fragile social systems becomes devastatingly high.
Okay, so let's pause here. If the physics of molecular vibration are this unshakable, If the supercomputer models are this precise, and the historical precedents of civilizational collapse in the Bronze Age are this alarming, anyone listening to this has to be asking the obvious question.
Why aren't we doing more?
Right. Why is the policy response moving so incredibly slowly? If the data is screaming at us, why aren't we treating this like the immediate structural threat it actually is?
Well, to truly understand that, we have to move out of the realm of atmospheric physics entirely and into the realm of political economy. The massive gap between scientific reality and policy action is arguably the most consequential disconnect in modern human history, and it is driven by a few very distinct, deeply entrenched structural problems.
The first one being a massive mismatch in timelines, right?
Mm-hmm.
The way we govern ourselves is fundamentally out of sync with the way the planet operates.
Exactly. Political systems run on very short, immediate cycles, 2 to 4 years for most democratic elections. Politicians are heavily incentivized to deliver immediate, visible benefits to their constituents.
Because they want to get reelected.
Exactly. But climate consequences unfold over decades and centuries. If a politician implements a strict, economically costly policy to heavily reduce emissions today, like, say, a massive carbon tax, the economic disruption and costs are felt immediately by the voters.
Gas gets more expensive right now.
Right. But the climate benefits of that policy, the droughts avoided, the sea level rise mitigated, won't be visibly realized for decades long after that politician is retired or dead. It requires asking society to pay a steep, upfront, tangible cost for a deferred, invisible benefit, which is historically very difficult to achieve in a short-term political cycle.
That makes a lot of sense. It's a fundamental flaw in human psychology and our political architecture. But we also have to acknowledge that this delay isn't just a natural quirk of human nature. There has been a concerted, heavily funded effort to actively delay action.
Yes, there has.
Now, we want to be incredibly clear and objective here. This isn't a partisan attack or a conspiracy theory. This is simply what the documented historical legal record shows. Researchers and historians like Naomi Oreskes and Jeffrey Superin have done incredible archival work on this. And what their research revealed is that the fossil fuel industry utilized the exact same playbook, and sometimes even the exact same public relations firms and scientists as the tobacco industry did in the 1960s and 70s.
The strategic goal was not necessarily to prove the climate science mathematically wrong, because they knew they couldn't.
Right.
The strategy was to manufacture uncertainty. The internal subpoena documents from major fossil fuel companies show that their own internal scientists thoroughly understood the physical reality of greenhouse gas forcing as early as the 1970s.
They knew.
They were actually factoring sea level rise into the engineering of their own offshore drilling rigs. But publicly, they implemented a multi-pronged, highly sophisticated strategy to delay regulation.
So what exactly did they do? How do you manufacture doubt when the physics are completely settled?
They funded a small handful of contrarian scientists to continually publish dissenting opinions, creating the illusion of a raging scientific debate. They heavily funded policy think tanks whose primary output was doubt manufacturing content, specifically designed to make the public and legislators feel like the science was still unsettled and that acting prematurely would destroy the economy.
Just muddying the waters.
And simultaneously, they engaged in massive private lobbying efforts against binding climate legislation, even as they began to publicly acknowledge the reality of the science decades later. The tobacco industry famously wrote in an internal memo, "Doubt is our product." The fossil fuel industry adopted that exact mantra.
They didn't need to win the scientific debate. They just needed to create enough fog and confusion to maintain the profitable status quo. And it was wildly successful. It bought them decades.
It did.
But even if we strip away the manufactured doubt, there is a fundamental structural nightmare at the international level. Think about it like the ultimate worst-case scenario of a group project in school.
Oh, I hate group projects.
Right. In a group project, everyone wants the good grade, but nobody wants to be the one who stays up until 3 a.m. doing all the actual research and writing. The atmosphere is a global commons. It doesn't have borders. If one country spends trillions of dollars completely revamping their energy grid to zero emissions, bearing all the economic friction and disruption, the entire world shares the benefit of that slightly cooler climate.
In economics and game theory, this is known as a collective action problem, or a variation of the prisoner's dilemma. Every single nation is economically incentivized to free ride on the expensive mitigation efforts of others.
Let the other guy pay for it.
Right. If you cut emissions, I benefit, so I will wait for you to do it. This is why international coordination is so painstakingly difficult. The Paris Agreement in 2015 is a perfect example of this dynamic.
Oh, so?
It is the most ambitious international climate agreement achieved so far, miraculously uniting almost every country on Earth. But how did they actually get everyone to sign the document? By making the commitments entirely voluntary.
There's no enforcement.
There is absolutely no binding legal enforcement mechanism. Nations submit their own targets called nationally determined contributions, and there is no tangible penalty if they fail to meet them other than international peer pressure.
So navigating this incredibly complex web, the unshakable physics of molecules, the terrifying history of fallen empires, the structural economics, the manufactured doubt, the international game theory gridlock, it requires having the right tools.
It requires a lot of context.
It does. You can't engage with this topic if you don't understand the language. And specifically for you, the listener, it requires having the right vocabulary. Because the words we use to describe these things are highly contested, and understanding them is practically a requirement for being an informed citizen today.
Vocabulary is absolutely critical because language subtly shapes how we perceive the solutions. If we look at the modern English vocabulary surrounding climate change, we can broadly categorize it into 3 distinct groups: scientific terms, policy terms, and contested or emotional terms.
Let's start with the science terms, because politicians and commentators throw these around a lot without actually knowing what they mean. We've talked about the greenhouse effect and climate sensitivity, which, as a reminder, is the specific mathematical calculation of how much warming you get if you double CO2. But what about words like forcing, feedback, and carbon budget?
These terms have rigid, specific mathematical meanings in physical science. A forcing is an external push on the climate system, like a change in solar radiation, a massive volcanic eruption, or an increase in human-emitted greenhouse gases. It forces a change in the energy balance.
Okay, a push.
A feedback is a secondary process that is triggered by the initial warming. It then either amplifies the warming, a positive feedback like the melting permafrost or the melting ice lowering the Earth's albedo, or it dampens the warming, which is a negative feedback.
And a tipping point.
A tipping point, as we discussed with the AMOC ocean current, is a critical threshold where a tiny additional forcing can push a complex system into a completely new, irreversible state.
And the carbon budget. I hear this one all the time.
The carbon budget is crucial for policy. It's essentially just an accountant's ledger based on atmospheric physics. It calculates the exact maximum amount of carbon dioxide humanity can emit in total, cumulatively, before we mathematically blow past a specific temperature limit like 1.5 degrees.
It's a fixed number.
It's a finite shrinking number.
Exactly. Now, contrast those highly specific physical science terms with the policy terms. These describe human interventions, our economic and technological responses. The 2 biggest ones you will hear are mitigation and adaptation. Mitigation means stopping the bleeding. It is the reduction of greenhouse gas emissions to prevent further warming. Building solar panels, transitioning to electric vehicles, stopping deforestation, that is mitigation.
Right.
Adaptation, on the other hand, means learning to live with the damage that is already mathematically locked in. It means building higher seawalls, developing genetically modified drought-resistant crops, or intentionally moving coastal populations inland.
This is a really important distinction because for a long time in the environmental movement, talking about adaptation was seen as a taboo, as essentially giving up. But now, because we've delayed mitigation for so many decades, the scientific consensus is that we have to do both simultaneously. We have to mitigate to avoid the unmanageable and adapt to manage the unavoidable.
That's a great way to put it.
Then you have policy terms like carbon pricing, which is an economic tool to make polluting financially expensive, forcing the market to adjust. And the heavily used terms net zero versus negative emissions.
What is the actual difference there? Because net zero is on every corporate brochure right now.
Net zero means a company or country might still be actively emitting some carbon, but they are pulling an equivalent, mathematically equal amount out of the atmosphere, say, by planting massive forests or using direct air capture technology, so the net addition to the atmosphere is zero.
Okay, and negative?
Negative emissions mean you are pulling out more carbon than you emit, actively shrinking the total historical amount of CO2 in the atmosphere.
And finally, we have the contested, rhetorical terms, words like catastrophe, climate emergency, crisis, or on the other side, denialism or alarmism. These are not technical peer-reviewed terms. They are rhetorical tools used to convey urgency, moral weight, or to delegitimize political opposition.
Which leads to perhaps the most important takeaway of this entire vocabulary lesson and a core skill for climate literacy.
Yes, the vital insight here is learning to distinguish between the physical science and the policy response. The physical science, the physics of greenhouse gases, the reality of the warming trend, the isotopic chemical barcode proving human attribution is extremely strong, mathematically proven, and not meaningfully contested in the global scientific community.
The laws of thermodynamics do not care about political affiliation.
However, the policy debates, how exactly we should transition our complex global energy systems, who should bear the economic costs, how fast we must move, what economic trade-offs are acceptable, those are genuinely complex, messy debates. They involve competing human interests, harsh economic realities, and deeply held ethical values.
Knowing when someone is deliberately confusing a scientific physical claim with a political policy preference is the ultimate superpower for navigating this topic.
Oh, totally.
If a politician or commentator says, we shouldn't implement a carbon tax because it will hurt the working class, they are making a valid economic policy argument. That is a completely legitimate space for democratic debate. But if they say, we shouldn't implement a carbon tax because carbon dioxide doesn't actually trap heat, they are fundamentally misrepresenting established 19th century physics to support their modern policy preference.
Exactly. Recognizing that difference allows you to engage with the actual, incredibly difficult challenges of the energy transition, rather than getting bogged down in fabricated bad faith debates about settled science. Okay, let's pull all of this together because we have covered an immense, staggering amount of ground today.
We really have.
We started by looking at a freezing, deep-time Earth, proving that greenhouse gases have always acted as the master control knob for the planetary thermostat. We looked at the sheer brilliance of 19th century physicists like John Tyndall with his brass tubes and Svante Arrhenius doing complex climate math by lamplight, mathematically proving exactly how molecular vibration traps heat.
A century ago.
We read the literal memory of the planet in the 800,000-year Antarctic ice core records, realizing that human civilization only exists because of the bizarre, anomalous stability of the Holocene, a stability we are now violently disrupting. We traced the chemical barcodes that prove this disruption is undeniably our doing. We looked at the fallen, shattered empires of the Bronze Age as a stark historical warning of what happens to complex supply chains when climate stability breaks. And we navigated the modern political gridlock, from the tobacco playbook of manufactured doubt to the economic nightmare of the global group project.
It is a profound, deeply interconnected story. It weaves together the mechanics of geology, the rigid laws of physics, the fragility of history, and the complexities of human nature.
But I want to leave you, the listener, with one final lingering thought. Something we haven't explicitly said yet, but which sits at the very core of this entire discussion, and honestly, the core of how we should view our place in the universe. We hear the phrase saving the planet all the time, but Earth, as a giant ball of rock and magma spinning in the vacuum of space, is going to be perfectly fine.
The planet will survive.
It survived a toxic, suffocating methane atmosphere. It survived being completely encased in miles of ice during Snowball Earth. It survived the apocalyptic meteor impact that wiped out the dinosaurs. The planet has all the time in the world. It has billions of years left to recover, to stabilize, and to evolve entirely new, beautiful ecosystems long after we are gone. The planet itself does not need saving.
No, it doesn't.
The climate crisis is entirely, 100%, a question of whether the highly specific, incredibly fragile Holocene conditions that allow human civilization to thrive will survive us. So the question we face today isn't whether the planet will endure our atmospheric experiment. The question is, what will the ice cores drilled 1 million years from now say about the fossilized remains of the 21st century?
That is a profoundly clarifying question to carry forward as we navigate the coming decades.
Thank you so much for joining us on this massive, sweeping deep dive today. Keep questioning, keep exploring the mechanics of the world around you, and we'll see you next time.